Good afternoon.
Good afternoon.
Hello. Hi. All right, so for today's presentation, you're going to have my typical writing utensil. We'll have one contrast color to do our bars between topics. And today, I'm going to have two different colors of ink going on because we need to be able to see the differences between a couple things that look really, really similar. So I'm going to be using color to do that. If you have different colored pens or highlighters, I recommend that you pull them out now and make use of them. If you do not have those items and you would like to use different colors, you're welcome to the pencil colors, colored pencils, however you say that, over there on the shelf. All right, let's go ahead and get started. Get this party started. All right, take a moment, update your title and your header and your objectives. Yep. This is the section that I skipped. Sorry. Our objective today is we're going to be calculating different measures of different segments that you find inside of circles. We're going to be using some algebra and the definitions of circle vocabulary in order to make that happen for you today. All right, let's talk about the first item. We only have 3 today. So the first theorem that we're going to be talking about is secant theorem number 1. Secant theorem number 1 states this: if 2 chords intersect inside a circle, then the products of the measures of the parts of the chords are equal. We're just going to go straight through the definition, then we'll draw the picture right underneath. Two chords intersect inside a circle, then the products of the measures of the parts of the chords are equal. There's going to be a lot of nested ifs in these today because they're trying really hard to be very specific about what it is that they're talking about. And sometimes when we try to go for that level of being very specific, the wording of it gets kind of lengthy and weird. Okay? All right, so let's give this a draw. Our setup is that we have 2 chords, we have them intersecting, and that happens inside of a circle. So I need to start with a circle. Badly drawn circle, if you would please. There's your badly drawn circle. And then we need some chords inside of it, so just get some chords. There you go. Doesn't have to intersect in the middle of the circle. This can happen anywhere in the circle you want, as long as the intersection is inside of the circle. Definitely need some names so we know where we are in this diagram. So 5 letters, please, go.
C, T, U, O, T.
All right, there we go. C-O-U-R-T, spells court.
Oh, yeah.
It just happened that way. Good job, guys. All right, so here's what this theorem is saying. We have the setup, the hypothesis, and so the conclusion is the products of the measures of the parts of the chords are equal. So here's one chord from C to U. Here's one part of the chord. Here's the other part of the chord. And this is why the colors are going to be important for you guys if you're easily confused on things like this. So we have this segment piece right here, CR, that part of the chord, times UR, that segment part of the chord. And that's going to equal this other segment piece here and this other segment piece here. So this part of that other chord, OR, times this part of the other chord, RT. Questions on this? Our setup looks okay? Seems pretty straightforward and simple? All right, you'll see how we use this when we get to the walkthrough. All right, let's look at the second theorem that we've got going on today. This is secant theorem number 2. It says this: if two secant segments are drawn to a circle from a common exterior point, then the products of the measures of the parts of the secant segments, of one secant segment, the product of the measures of the parts of one secant segment is equal to the product of the measures of the parts of the other secant segment. And again, this is another moment of mathematics needing to use the English language to try to be as specific as possible and giving us a bunch of nested possession, that things belong to other things. Yes, I'll give you guys a couple moments to make sure that you have it down. All right, let's go ahead and give this a draw. Our setup says if two secant segments drawn to a circle from a common exterior point. So I need a circle, I need two secants, and I need those secants to come from some point outside of the circle. All right, so start with your badly drawn circle. Have some point outside of the circle. And then we're going to draw some secants from that point. So it doesn't matter where they go through the circle, as long as they connect to the circle in two spots. Okay, these aren't tangents. Tangents only hit in one. This is a secant, it has to hit in two. Once again, I need some road signs to help me out here for the next part, so please name these 5 points. Another voice.
Okay.
Okay. L or M? L. I heard A. In the back? B? Like boy? All right, so there we go. There are our points. Looks like it spells Blakey. Blackie, okay. All right, so here's what the conclusion of this theorem says. The product of the measures of the parts of one secant segment, okay, the product meaning multiplication, the measures of the parts. So if I look at this secant segment, this would be one part, this would be the other part. And so the measurements of that first part times, that's supposed to be a multiplication, the measurements of the other part of that secant equals, we look at the other second segment, yeah, exactly. And we multiply the measures of those segments. Okay. So you're taking the different pieces of the one of the segments, and you're multiplying them together. Whatever you get, you're going to set equal to the multiplication of the parts of the other segment. Okay? All right. If you have at least as much space as you used for secant theorem 1, maybe about 6-7 lines on your paper, you could continue. If you've got a little bit less than that, you may want to write small or join me on the next page. All right, this is the final theorem for today before we go on to the walkthrough. This is the tangent secant theorem. It's the only one of its kind. It says this: if a tangent segment and a secant segment, walk into a bar, are drawn to a circle, from a common exterior point, then
Is it drawn?
drawn. Then the square of the measure of the tangent segments is equal to the product of the measures of the parts of the secant segment. Again, I'll give you guys a couple moments to get that down, paying really close attention to all those of.
A little loud here.
It is. It's loud today. They must. All right. So I'll read it out loud for you so that you can read your thing and find out where we are. Yes. Okay. If a tangent segment and a secant segment are drawn to a circle from a common exterior point, then the square of the measure of the tangent segment is equal to the product of the measures of the parts of the secant segment. All right. I know. So it's a lot of ofs. It's wordy. It's wordy, and it's wordy because we're trying to be really specific with which segment, which parts, what we're measuring, what we're adding or multiplying or subtracting or whatever we're doing. And so again, it's that moment of, in an effort of being very specific, it gets really wordy and long and looks way harder than it actually is. All right, let's draw it. Looking at the setup, I need a tangent, I need a secant, I need a circle, and I need some sort of common exterior point. So we're going to start with the circle. So there's my badly drawn circle. I need some sort of common point. There's my common point. And then I'm going to take the straight edge that I'm improvising with today, the pack of nurses' passes, and I'm going to draw a tangent looking line. And then the same straight edge, I'm going to draw a secant looking line, and so our figure looks a little something like that. Once again, I need some roadmap, so can I please have 4 letters? S.
T.
T.
U.
K.
U and K. All right, welcome to Stuck. All right, the conclusion of this if-then statement, this theorem says, the square of the measure of the tangent segment is equal to the product of the measure of the parts of the secant segment. Okay, let's start with the first one. We're going to start at the back part, the tangent segment. Where's the tangent segment? The KS, because that's the only one that touches the circle in one spot. So this is my tangent segment. I need its measure, KS, and I'm going to square it. So this is the square of the measure of the tangent segment. That is equal to, the next part of the sentence reads, the product of the measures of the parts of the secant segment. So my secant segment is US. The parts of it are UT and TS. And I'm going to take their measures, UT and TS, and I'm going to multiply them because it wants a product. So far, so good? Any major questions on what you saw? All right, let's do the quick walkthrough so that we can see how we might apply it. If you haven't already, make sure that you grab 10.3. They're over by the calculators. I'm going to move this off to the side in case you need it. All right. My version looks a little different from yours because I'm using the large font version so that it's easier to see up on the projector screen. It just means that mine are in a slightly different location on my paper. All right, the directions, I think something happened. The directions got chewed on. It says find x, the value of x, and round it to the nearest tenth if necessary. Assume that the segments that look tangent are in fact actually tangent. All right, so look at number 1. What kind of setup do we see on number 1?
The secant theorem.
Secant theorem.
Number 1.
Secant theorem number 1. There's a circle, there's 2 chords, and these chords intersect somewhere inside the circle. According to the theorem, it says that you're going to take this piece. Now, notice the intersection point doesn't have a
I
name.
want to say that. Is it X since it's
It can be any letter you want it to be. So go ahead and pick your favorite letter of the alphabet now that isn't already on diagram number 1.
E.
And go ahead and name that your intersection point. Then, from K to the intersection point, that measure, times the intersection point to M, that measure. That quantity, whatever it is equal to N to the intersection point, whatever you named it, times the intersection point to L. Okay, so write your setup. We'll do the calculations later. All right, look at number 2. What kind of setup? This exact same one, secant theorem number 1. So you're going to follow the same pattern. Look at number 3.
Secant theorem number 1.
Same thing. All right, turn the page on to the back. Take a look at number 4. Which setup do we have? Number 2, secant theorem number 2. Remember, secant theorem number 2 says each secant segment, so you have to identify your secants. In this case, C to L is one secant. L to N is another secant. Excuse me. The theorem says this part right here, the chord, times that exterior part of your secant, this other piece, is equal to the same portions on the other secant. Okay? So then, set up your equation and you'll solve it for x. Take a look at 5 and 6.
Tangent secant.
Exactly the same for 5 and 6.
Oh, no.
Third page, looking at 7, 8, and 9. tangent secant theorem. Remember that on tangent secant theorem, you're going to square the tangent. So on number 7, which segment is tangent?
RT.
RT or TR. Very nice. On number 8,
LG.
LG or GL. And 9,
HL.
HL or LH. Alrighty, very good. That is all that we had for you today. Thank you very, very much.